then let's do share screen. Yeah, it all works. Yeah, it does. Okay, so how are you? So I'm going somewhat slower than I was hoping, really, but I think it's fine. My goal.
תודה רבה.
מה?
לא, אני דיברתי פה עם מישהו.
Okay, if you want to have discussions which are not part of the lecture, then please close your microphone or don't be close nearby. Okay, so I'm hoping to complete the introductory part today, which means that then I'll give you the tutorial on Tuesday, and you also get the next problem set only on Tuesday. So I don't know if you should be thankful or not for that, but that is the general plan. And then we could discuss things starting to going into more technicalities next week. So a brief recap. So last time we spoke about Feynman diagrams, which are the key tool of calculations in particle physics. It's really an introduction to Feynman diagrams. So we spoke that the main, the key factor in the Feynman diagram is the vertex, the vertex, yeah, vertices, right? That connects the particle with the gauge, connects the leptons with the relevant gauge bosons, and this is the way that mediates the interactions. We said that there are several key properties of vertices, right? For example, the electromagnetic one. This is a location which we can think of as a location in which particles are created and destroyed. So the way to think of it is that we had a particle, an electron in this case, and then at a certain point in space-time, this electron is destroyed and a new electron is produced and a new photon is produced. This is the way we describe as the emission of a photon, really. Okay? No, I think the other ones were better for right now. Let's do those. Okay, now at every vertex, right, there are some key features that are conserved, especially the form momentum is conserved. Right, P1, so if this form momentum here is P1 and this P2, and this is typically called Q, then we have P1 mu equal P2 mu plus Q mu. Now there are many other conserved quantities. We'll go through a partial list today and a full list in the tutorial of all the conserved quantities, which determine what interactions can happen, right? But of course, not only does the form momentum, also angular momentum, leptonic number, baryonic number, what's called strangeness, what's called parity, many things that are conserved in each vertex. We added the arrows. They represent the flow of charge. Now, an electron, I will denote with the same arrow, but with the opposite arrow. Okay, this will be an E plus. So arrows represent conservation. It represents the flow of charge. And also for each type of interaction, there is a coupling constant associated with each vertex. So the coupling constant is denoted normally by G. Right. So for each type of interaction, there is an associated coupling constant. From the coupling constant, we calculate measurable quantities, right? We'll calculate the quantum amplitude, and eventually from that we will calculate the probability of an event to happen, the decay, the lifetime of a particle that decays, etc. So we said that a physical process, such as scattering or annihilation, is represented by an exchange of virtual particles, right? So for example, a scattering process would be represented by an exchange. If it's an electromagnetic scattering, it will be represented by an exchange of a virtual particle. This will be a photon in the case of electromagnetic, so this is the QED. I describe Mandelstone variables. Again, these are useful computational tools, and they represent different diagrams, right? The space-like, time-like. There is a U channel, which I'm not sure what it means, right? So the S channel would be exchange of a virtual particle, so P1 and P2. So basically we have an annihilation here, right? You have an electron, let's say, and an anti-electron that annihilate, producing a virtual particle, and then produce two new pairs of electron and anti-electron. So we can think of that as a scattering process, right? You come up with an electron and anti-electron, you end up with an electron and anti-electron. Right? But the way this scattering happened is that there was an annihilation, production of a virtual photon, with momentum q, and then this photon again produced pairs. This is called the S channel. There is the T channel, right? Which is essentially the same, right? So we have a scattering, let's say P1, P2, P3, P4, and Q, right? It's called the T channel. And there is a U channel, which is the same as the T channel, but with the exchange of the outgoing particles momenta. So it's relevant only in cases where the outgoing particles are identical. So it's less available generally than the other two. Right, so we have P1, P2, and then this will get into P4 and P3. It's a U channel. And we define the variables, the S, P1 plus P2 squared, which is P3 plus P4 squared. The T is P1 minus P3 squared, which is P4 minus P2 squared. And the U is P1 minus P4 squared, which is P3 minus P2 squared, right? These are all Lorentz scalars, so they get the same result, the same value in every frame. In particular, we show that the Lorentz invariant quantity, so square root of S, is nothing but the total energy. Is the total energy in the center of mass frame. Now I mentioned also that Feynman diagrams are really a perturbative diagrams, right? So in the sense that if you want to calculate the probability of scattering to occur, right? Or the cross section to be more precise, right? Then what we have to do, we have to sum up over all possibilities. So for example, if we're talking about scattering, electromagnetic scattering, so we have electron and electron coming, they can exchange photon and being scattered. But we can also think of the possibility that they may exchange two photons. Right? So really what we have to do, we have to sum up over all possibilities. And there are infinitely many number of those. But fortunately for us, right, since each vertex gives this coupling constant G, we said that the matrix element, the quantum mechanical transition matrix element for the interaction, M, here will be proportional to G squared. Here will be proportional to G to the power 4 because we have 4 vertices, right? And the interaction probability we do this calculation more precisely, I think, next week, or at least we start doing it next week. It might take us more than a week to do. Gamma is proportional to M star. So this is M squared, is proportional to G, but here to be to the power 4, right? If I'm referring to that one. So as long as G is small, then the higher order terms are just perturbations. So for the electromagnetic, G is indeed small. We don't normally use G, we refer the term alpha, which also has the name coupling constant, and is proportional to G squared, and alpha for QED is Q squared over 4 pi epsilon 0 H bar C. This is a dimensionless number, which is 1 over 137. That's also referred to coupling constant. So it is indeed small, right? So the next term, right, the one with exchange of 2 photons, would give a correction of less than 1% to the calculation which we do in if we only take the first order. And of course, the third order would be 1% of the second, etc. So this is quite handy, and it works very nicely for QED. It also works okay for the weak interactions, although the weak interaction coupling constant is larger. Alpha weak is about 1 over. But since in the weak interaction we have to produce massive particles, right, gauge bosons, the W plus minus or the Z, and they are very massive, right? The mass is of the order of 90 GeV. Then the probabilities decrease also according to the mass, of course. So it is going to be very weak. So the effective coupling constant weak coupling constant is much smaller, something like 4 or 5 orders of magnitude smaller. So something of the order of 10 to the minus 7 to 10 to the minus 6 or so. So it is indeed very weak. However, when we speak about the strong interaction, then we do run into a problem because alpha strong is of the order of unity. So we cannot really use perturbation approach because we do have to sum over infinite terms. The contribution from each one is going to be of the same order as that of previous ones. But what saves us is that when we go to higher energies, then the coupling constant is not really a constant. It's really a misleading term. It is energy dependent. The for the strong interaction actually goes down with energy. So when we go to higher energies, it becomes smaller. I'll show you, well, at least I'll give you some sketch. You can find it in textbooks. Exactly. Okay, I think this is as far as we went through last time. I want to continue and hopefully complete today the introductory part of the standard model. But before I can do that, I want to stop and ask you if you have any questions. No questions? Okay. Again, I won't give you work today until we finish that. And when we finish that, I'll give you the homework. So it will be likely on Tuesday that you get homework. So decays. Really, it's a decay via the weak interaction. So I told you that nearly all the particles that we see and we know of, they are actually not stable. Most of them decay, and over a very, very short lifetime. That means that detecting particles is not that easy, because we can only detect those particles that are not decaying over long enough scale that they can be seen. If they detect before they can be seen, then we don't see them. We can just see their outcome. Now, what are the conditions for a particle to decay? So in order for a particle to decay, we must have conditions. So the first is that it can decay into a final state of a lower mass, right? If it doesn't have a final state with a lower mass, it cannot decay anywhere. That's why the electron is stable, and muons and tau are not. So it has a final state with lower total rest mass. And it can reach that final state by a process which can be constructed by the relevant standard model vertices in the Feynman diagram, right? A proton is heavier than an electron, but it cannot decay into an electron, because there are certain conservation laws that each vertex must meet, and because of these conservation laws, it cannot decay into the electron, right? So we said that it can be reached, that the final state can be reached by a process constructed from standard model vertices in Feynman diagrams. Right. Now, the same as we did with the examples I gave on Tuesday about QED vertices, right? To construct the physical processes of electron-positron annihilation and electron-electron scattering by exchange of a photon, we can do the same, using the basic vertices of the weak interaction and the strong interaction, right? The quantum chromodynamics. So let us look at an example, right? We can look at decay of a muon, right? Muon decay. So we have a muon, the charged particle, and it can decay into an electron, anti-electron neutrino, and a neutrino muon. Right? This is done by the weak interaction. Right? Since the muon is heavier than all the rest, then it's okay. So it will decay. How would we describe the decay? So you start with the muon. And then we have a vertex where it now exchange the W, right? It has to be charged. So we have the W boson and the muon neutrino. And then the W boson, right? Now it can decay or interact and produce an electron and an anti-electron neutrino, right? So the W minus boson is charge carrying boson. So we have here conservation of charge, right? In each vertex, we have two vertices. We have conservation of charge each. We also have conservation of electron leptonic number. So that's why we have electron and an anti-muon. We can think of that as electron and muon carrying an electron leptonic number, and conservation of muon leptonic number. That's why we have the positive neutrino muon. Okay. Now, since the electron, of course, is the lightest, then we have no way of continued decay the electron, right? Because any other decay would not conserve energy and momentum when we go to the center of mass. Right, so as a result, the electron must be stable. Electron is the lightest lepton, so it is stable. Now we can have the same diagram exactly for the tau lepton, right? So rather than muon, I could write it down here, tau, right? And this will be a neutrino tau, right? But so this is, I could write it, and the rest looks the same. Only difference is that because the tau is heavier than the muon, then the outcome of the decay of a tau could be both the electron and the anti-neutrino electron, but also the muon and the anti-neutrino. Right, the tau has two to decay. Is that clear? Simply because the tau is heavier, right? So we can always go to the center of mass. Then it can decay both to the muon and to the electron. Now we can say the same about quarks, right? So rather than muon or tau, I could write down the same, exactly the same Feynman diagram for the decay of a quark, right? Down, up, W, boson, and then electron and neutrino electron, anti-neutrino electron, right? Again, I conserve the charge, right? The down quark has a charge of -2/3, up quark plus 1/3, W minus is charge is a -1. So charge is conserved in each vertex. Also, the baryonic number is conserved. It's the same generation.
Isn't this the same diagram essentially?
It is exactly the same diagram.
I mean, is this describing the same process, just with another up and down that are not taking part of it?
Exactly, this is exactly the same process.
Okay.
Right? Well, I'm cheating, right? Why am I cheating? Okay.
That's another beta decay.
That is, yeah, this is a beta decay. Well, yeah, exactly. I'm cheating because the upper process, the decay of the muon or the tau into neutrinos and electron, or in the case of tau, neutrino and muon, this is something which we can see in nature. This is something which we observe to happen. the decay of a down quark into an up quark is not something that we see in nature as I plotted. The reason is that because of the nature of the strong force, quarks don't go as free particles. They're always bound particles. But if we have the down quark can be bounded to another down quark, and to another up quark, if you remember, what is a combination of up, down, and down?
Neutron?
This is a neutron, that's correct. And what is a combination of an up, down, and up?
Proton.
This is a proton, right? So what's really described here is that a neutron, right, decays into a positively charged proton plus an electron plus a neutrino electron, antineutrino, right? And this, of course, is neutron beta decay. It's the nuclear. Right, it's a radioactive decay. But in terms of the basic process, you're saying it's exactly the same process of the decay of the muon. Right? In the case of quarks, we simply do not have free quarks. I'll say a few words about that in shortly. Right. This is the nuclear beta decay. Again, it's a weak interaction decay. But the process is the same as we had previously. Okay. Questions? Okay, no questions? Okay, then. Let me talk about mesons. So again, there is a lot of jargon going on here. So, we just described how a neutron decay into a proton, right? So we have particles, since quarks don't come together, right? We have a combination of 3 quarks, and these are known as baryons, right? So particles made of 3 quarks are known as baryons. It comes from Greek for heavy, because they're heavy. Leptons are particles that do not contain any quarks, right? Particles with no quarks are generally called leptons. Right, again, from Greek, it's light. And we can also have a bound states of quarks made of 2 quarks. Sorry. Basically a couple of, Particles made of 3 quarks are known as baryons. Particles that don't have are called leptons. So we have particles that are made of bound states of a quark and antiquark. Particles made of a bound state of quark, antiquark are called mesons. So this means intermediate mass, right? And then together, bound states of quarks, so baryons and mesons, are collectively known as hadrons. So hadrons is a combination of baryons and mesons. And really, this is a bound states of quarks. Okay, so mesons are intermediate, right? They have intermediate masses in between the baryons and the leptons. So we discussed earlier last week, I think it was. Now I'm going to tell you something which may look a little bit strange, but then you think of it after a while, you see it's not that strange. Okay, so the neutron and proton, they look like nearly identical particles, right? So the neutron have, two ups, one up and two downs, and the proton have two ups and one down, right? So they are nearly identical. And so it is suggestive that both are really two different manifestations of the same particle, which is called nucleon. And this is an analogy, to the two states of the electrons. We know that the electron has a spin, right? We have a spin up and spin down, but we don't call these two different electrons. We call these one electron we spin up and one electron we spin down, right? So indeed, when we look at the mathematical structure of neutrons and protons, they are very similar to the mathematical structure used to describe particles with spin up and down. So we just call them as a single particle called a nucleon. And difference, rather than spin up and down, it's called isospin. Right, we'll have a more thorough discussion and explanation about that later. So since protons and neutrons are very similar in many ways, we treat them as two manifestations of a single particle, which we call the nucleon. Right? And the difference resembles that of spin up, down electrons. So is quantified by the term isospin. In fact, mathematically, the mathematical structure of an isospin is identical to the mathematical structure of spins when we describe it. So, within this framework, we say that each nucleon, we basically postulate that it has an isospin I of 1/2. So we postulate that each nucleon has isospin I equal 1/2, and then we simply repeat the same calculation that you're doing on the electron spin. If you did it in quantum mechanics, if you did not, then you will do it whenever you study quantum mechanics. Then we say that the spin up down, so it's I3, right? The one component of the isospin This will be plus minus 1/2, right? The plus half is for the proton and 1/2 into minus 1/2 into neutrons, right? So plus half is the proton and minus 1/2 is the neutron. Now this essentially translates into I3 equal to 1/2 for the up quark and minus half for the down quark. Alrighty. So now we can think of the mesons. The reason why I told you all that is not just that you know it, we will study it more in depth down the line, but now we can speak of the lightest mesons, right? So the lightest mesons would correspond to the lightest, to the bound states of the lightest quarks, right? So the lightest mesons correspond to the bound states of the lightest quarks. Right, so for example, for the pion, with the charge, right, it really, I can think of it as a state with I equal +1 and I3 equal +1. So it's really made of up and anti-down quark. And for the negatively charged pions, this will simply be I equal to 1 and I3 equal to -1. So of course it's the opposite, down and anti-up quark. And for the neutral pion, right, of course this would correspond to I equal 1 and I3 equal to 0. So now it's a linear combination, 1/√2 of up, anti-up, minus down, anti-down. Now I put two notices here. One is the minus sign that is here. It's again, it comes from the symmetry group from the SU2, because it requires that the anti-fermion transform in the same way as the fermions. In fact, it's a convention, and in some textbooks you'll find that for the pion plus you get a minus sign, minus up and anti-down quark. I refer you to the book by Halton and Martin. They have a discussion there at section 2.7 about where it comes from. I'm not sure it will be much more illuminating without going deeper into group theory. The other comment, sorry? So
May I ask a question?
Yes.
So you say that up and down have isospin 3 of ±½
Yes.
So, but they also carry I equals 1/2, right? Like total isospin.
Yes, correct.
So could they join to create something with total isospin of 3/2?
Yes, but this would not be considered the lightest one. I'll get to that in a second. This would be an excited state.
All right. No, if you get to that, I won't stop you. Thank you.
I'm going to get that. I'm going to get to that in 2 minutes.
Sure.
So I just said I had a comment about the sign here, which is really a convention. And then there is also an orthogonal state, right? Which you could think of an orthogonal state to the pion 0, right? You should naively write it as 1 over square root of 2 of u bar plus d bar. But actually, this is not the case because there is a better symmetry that works here, which is 1 over square root of 3 u bar plus d bar plus s bar. S is a strange quark. So this is the correct orthogonal state to the pion 0. And I won't go deeper than that at the moment. Okay, so the pions have masses of around 140 MeV.
Or DD bar without the strange is not orthogonal to the other three?
It is orthogonal. This is the orthogonal state to this one.
And without the strange, it's not orthogonal?
It will be orthogonal, but it is not with the same symmetry group. Right, this is within the group SU2, and this is SU3. This is something which I was thinking, I'm still thinking whether we should, how deep we should go into the symmetry groups. I'm still not sure. Depends how long we're going to have. So the mass of the pion, the charged pion is about 140 MeV. So in between the baryon's mass, right, which is of the order of GeV and higher. The neutral pion is slightly less massive, 135 MeV. Since this is heavier than the muon and the electron, then it means that it can decay into the muon and the electron. So we can have a decay of the form, let's look at the pion minus, right? So we have a down quark and an anti-up quark. So it's anti, so it has the opposite sign. Up, anti, and down. They exchange the W, and then they would decay into a lepton and an anti-neutrino lepton. So L minus can be either E electron or muon. But the pion is lighter, so this is of course the pion. Right, so this is a decay channel of the pion into electron and anti-electron neutrino or muon and anti-muon neutrino. Now, since it's lighter than the tau, then it cannot decay into the tau particle, but then we can reorder the Feynman diagram, right? So if we reorder it, we can describe the opposite process in which the tau can decay into the pion, right? So we can have just taking the same diagram, switching it, right? And we end up with tau that decays into a neutrino tau, and then a down and an anti-up, which together form the pion. Right, so it's the same diagram that describes both the decay of the pion and the decay of the tau into the pion.
I have a question.
Yeah.
The W particle is heavier than all of these.
Yeah.
Why can't it, decay into, like, if it becomes something as heavy as the W, why can't it decay to something that's lighter than him but still heavier than the pi?
The W is a virtual particle, right? So it is not, doesn't have to, we see the W as a free particle. We never see it as a free particle. Okay, so when you look at the process, right, you only see the again, remember that Feynman diagrams are computational tools, right? These are really a way of describing a process that happens. Now, what happens in reality, we're seeing a pion, right? This is the process that we're describing. A pion decays into an electron plus anti-electron neutron. Right? This is what we're seeing in the lab. We never see the W. This is a mathematical way of us for make quantitative calculations of the probability of that, of the lifetime. I'll show you how to calculate the lifetime of the pion. Now, since this is, in that case, what matters is that the energy, now we said that the energy must conserve because part of the form momentum has to be conserved in each vertex, right? And so we can never have that the total, you know, a particle cannot decay into particles whose rest mass energies are larger than its own rest mass energy, because you can always go to the center of mass frame. So, to the frame in which this particle is at rest, and you simply don't have enough energy. You cannot have conservation of energy if you try to decay a particle into heavier particles. All right. The important thing to remember is that what we care about, you have conservation of energy in each vertex, and the physics here that the particle can never decay. You cannot create energy from nothing, right? Energy must be conserved as part of the conservation of the form momentum. Did that answer your question?
Yes, thank you. I understand now.
Okay. So I had a question which was asked previously about ground states. So this is exactly what I want to describe. Oops, that's not this one. That's this one. About excited hadrons. Right. So we said that the pions are the ground state of a system which is made of quark and antiquark. Maybe I should write it down. Pions are the ground states of a system made of quarks, antiquarks. So in this system, we have that both the orbital angular momentum and the spin are zero, right? So L is equal to S equal to 0. And we can also think of this, as a wave function whose radial wave function is also in the ground state. So N is equal to 1. Now let me ask you a question. Did you study the hydrogen atom in quantum mechanics? Okay, who here in this audience did not study the hydrogen atom in quantum mechanics? Well, most of you have open cameras, and nobody I saw raise any hand. There are a few that don't have open cameras, and so on. No. If you have, then I simply have to assume that you studied it, so it's going to be pretty easy, because you know what I'm talking about. We have this YLM's expansion, and then we can speak of the ground state, and then we can have the first excited state, and we split the wave function into the radial part and the spatial part using the YLMs, right? So the radial part is in the ground state if N is equal to 1. And for the spatial part, it's L equal to S equal to 0. This is the ground state. So in exact analogy to the hydrogen atom, we can look at this combined wave function of up and down, or up and anti-down, or anti-up and down, right? As a quantum mechanical system, which doesn't have to be in the ground state. It can be in an excited state, right? So, we can have some property state. For example, so we think of the quark, anti-quark system, bound system. In analogy to the hydrogen atom, and consider excited states. Right. So for example, we can have a higher spin, right? So we have a spin. So we can consider a bound state of, let's say, the up and anti-down quark, right? Just with a positively charged pion. But now we have L equal to 0, but S equal to 1, and N is equal to 1, still in the ground state, right? So you can think of that as an excited charged pion with two spins pointing up. So pion plus with two spins pointing in the same direction. Right? But this is really a different particle, right? With a different mass. The different particle is called the rho. This is the rho plus. And the mass is much heavier than that of the pion. It's 770 MeV. Right? So the rho plus particle has the same ingredients, right? Basic, made of the same basic quarks as that of the pion, but both spins are the same direction. Now you can think of that, you can think of the mass difference, right, as really the hyperfine split. This is very analog what we're seeing in atoms, right? We have a magnetic interaction between the spins of the electron and the nucleons at the kernel, right? Now in hadrons, it's analogy, but the interaction is chromomagnetic, right? So it's much stronger. So it's not a hyperfine. In atoms, we're seeing that very small splitting, but in the difference in the masses between the rho particle and the pion is very strong, right? It's very large. So I'll just write it down: m rho minus m pion. The hyperfine state is hyperfine splitting.
So if the hyperfine constant is alpha 1/137, what's the
No, it's not. Alpha of 1/177 is the QED. Is for
the hydrogen atom hyperfine, the actual hyperfine.
Yeah.
So here I'll be replacing 1/137 by
No. This is a QCD because you have interaction between the quarks. So it's a strong interaction, and it's
order 1.
Much more than that actually, because I'll say a few words about that. Yeah, the order is 1, but you have multiple of them. So yeah. Okay. So that's why here it's not a small difference, it's a huge difference in masses. Right? It's nearly 4 times, more than 4 times, nearly 5 times bigger. So this is one example. The other example is orbital angular momentum. So again, just a quick example. I just want to give you the feeling of that what there is, right? So if we consider a state, again, a bound state made of an up and anti-down particle, right? With now we say L is equal to 1, S is equal to 0, and N is equal to 1. Then this is called a B meson. So it's known as a B plus meson. And again, it's much heavier. The mass of the B meson is about 1235 MeV. It's more than GeV.
Whenever you say spin, you mean isospin.
And no, no, I think this is the spin. This is the spin. It's not the isospin.
Actual physical spin, as in.
No, these
the
are the
thing
spin.
that-
This is the real spin. This is not the isospin. I did not talk about the spins of the. Okay, you're right that I did not mention that, but the quarks as well would have spins. Same as the electrons. I hope I'm not confusing you. I'll double check that. To the best of my knowledge, this is a real spin. And the last one that I wanted to mention here is the radial excitation. Right. So again, if we talk about the bound state of the U D bar, then we have L equal to 0, S equal to 0, but now N is equal to 2. And this has a name, it's called pi 1300. And it won't surprise you to realize that the mass of this pion is 1300 MeV. Now, obviously, these excited states are much more massive. So they are being observed much less frequent than the ground states. Often they are being ignored, at least today, but historically they did play an important role in producing the quark model. Now, this is just for the mesons, but very similarly, you can speak excited states of baryons. So, you know, excited baryons. Right. So, for example, the excited state of a UUD, which has L equals 0 and spin equal 3/2, and N equal to 1, right? The spin of the proton is 1/2, right? So 3 would be 3 as spin 3/2. This is known as the delta particle. So an excited state of a proton is called a delta. Right? It's excited in terms of spin. Now, of course, if you're not confused enough by now, then remember that what we did so far was just with the first generation quarks, the up and down. But of course, all the other quarks can participate as well, right? So we can have heavier mesons and heavier baryons made from heavier quarks, right? So in addition, we have heavier mesons and baryons, right? Not only from excited states of the lightest baryons, but also from heavier quarks. Right. So, you know, if we take the lightest strange meson, the lightest charged strange meson, then we end up with a particle which is known as kaon. So the kaon plus is made of an up and an anti-strange quark. And of course, the negatively charged kaon is made of the strange quark and the anti-up quark. Right? But this is the ground state. Right? We can have, for that kaons as well, we can have the first excited state. So kaons with S equal to 1, right? Spin equal to 1. They will be the first excited state, so they would be heavier. These are known as the K star, kaon star. Now, I refer you to what's called PDG. It's called particle data group. You can find all the information about all the particles. You can understand now that there are very many of them. Now you can start seeing how many. But as I said, you might feel more relaxed knowing that the vast majority of them are highly unstable and in fact decay very quickly. So the lightest hadrons we have are the pions and the kaons. So the kaons are the lightest hadrons. So these are the ones that are mostly produced and mostly observed in experiment. And of course, they have the longest lifetime. So these are the most easily one detected. The longest lifetime. But I think now you see the richness, right, from this 6 quarks. When you start exciting them, you can get very many different particles. All right, more questions? Okay, if not, I want to say now a few more words about quarks. Okay. So there are today very many experimental evidence for the existence of quarks. Now, interestingly, if you go back historically, you realize that people did not always believe in quarks. It took many years for people to believe in quarks, in the quark model. And the reason is that we do not see free quarks in nature. Not see quarks directly. Now, the reason why we do not see quarks, let me just write it down. Quarks do not appear as particles in nature. And the reason is explained by the hypothesis of what's called color confinement, which, they carry the strong force. The strong force is also known as the color force for some strange historical reasons. And the hypothesis of color confinement states that colored objects are always confined to color singlet state, right? No objects with a non-zero color charge can exist as free particles, right? So the wave function of a color carrying particle, which is the quarks and the gluons, is limited to the size of the proton, which is 1 Fermi, right? So the non-existence of free quarks in nature is explained by the hypothesis explained by the hypothesis of a color confinement. It states that colored object are always confined to colored singlet states. So in any observed hadron, right, the quarks are organized such that the hadron is color neutral. You know, the basic analogy is the atom, which is always electromagnetically neutral, right? Electrically neutral, sorry. Heuristically, you can argue that the colors of each quark cancel each other, right? So if there happened to be a quark that is free, you know, set quarks that are not color neutral, then they always reorganize themselves as a set of neutral hadrons, which occurs over a time of you know, one femtosecond or so. So quarks in nature, quarks organize themselves such that the hadron is color neutral. Okay, now I mark as a comment that there is no currently analytical proof of the concept of color confinement, but there is numerical proofs called lattice QCD and things like that. The key reason is that the gluons themselves do carry color. So qualitatively, right, if we try to do it qualitatively, right, let's say that we have, you know, let's say we have two charged particles, right? Charge, I mean electrons, right? And, you know, you have field lines which connects them, right? So this is very heuristically right way. Now, if you take them apart, right, the field line stretch, right? Well, they will spread. When taken apart, the field line will spread. Now, what happens if you try to take two quarks apart? Quark and antiquark. The quark and antiquark connect via gluons. But when you try to take them apart, what will happen is that the gluons, since they carry different colors, they can interact with each other, which is something that cannot happen in electromagnetism, right? So it's a qualitative picture, right? So it's a qualitatively. Since quark carry the color charge, there are attractive interactions between the exchange virtual gluons. This do not exist in QED. And the color field between the quarks is squeezed into a tube. So the outcome is that of this all squeezing is that when they're at relatively large distances, the energy density in the tube between the quarks is constant, roughly. That's an outcome.
This is because the gluons are also charged?
Yes,
With color?
yes. The gluons are also charged because they carry color.
Because you wrote down that the quarks carry color.
The quarks carry color and the gluons carry color as well. This is because, it's a good point, is because the gluons carry color as well. As an outcome of this squeezing, the energy density, again, it can be shown, blah, blah, blah. I'm not going to give you the full mathematical proof right now. The energy density in the tube between the quarks containing the gluon field is constant. So the total energy stored in the field is proportional to the separation of the quark. So giving a term of the potential, so the potential is of the form V of R is constant times R. Now, when the constant K is of the order of 1 giga electron volt per femtometer. So in SI units, right, 1 GeV per femtometer is 1.6 times 10 to the minus 19 joule times 10 to the minus 15 meters. Did I miss something? I have to check the units later on. I just marked them myself. No, that's fine. And that is 1.6 times 10 to the 5 Newton. That's an extremely large force when it acts between two fundamental particles. So what would happen if we insist and we try to pull apart two quarks from each other? Obviously, we cannot take a rope and tie it to the two quarks and try to push. That's not going to work, right? The way we try to do it is to simply take, let's say, a proton and bomb it with energetic electrons, right? So in some cases, an electron would be transferring a momentum into one of the quarks in the proton, and it will pull it away from the rest of the quarks in the proton. Right? That's what's being done. Right? So when the distance between this quark that is being pulled, right, and its other two friends becomes of the order of a femtometer, then the energy of the gluon tube becomes large enough to produce a new pair, quark and quark. Right. So what will happen is that we have these. Let's say we have an up quark, and then we have right up quark, up and down quark, right, up, down, right, and the quarks are glued together by the gluons. So this up quark is being taken away, right? So it will be glued and it produced, right, the up quark. It would produce a pair of a down bar and down quarks, for example. Right? Can be anything, right? I just had an example, a pair of a down antidron, right? Now the strong interaction would bound one of these newly formed quarks to the original quark, right? And the other one to the friends. So what really happens in this case, remember we had a knockdown of this up quark with, let's say, an electron, and it's being kicked off, and then it produced a pair of a quark antiquark, and then one of these quarks will be attached to the quark, and another one will be attached to the rest of the quarks, the original quarks. So we end up producing a new meson. Right, this is the charged pion, and this is a neutron. Right, so that's really what happens, right? We try to pull away a quark from its friends, then we end up producing mesons. Now, of course, if you could do it slowly, you could produce many mesons, right? But of course, we cannot do it. What we really do is to just give the quark a large amount of kinetic energy by just bombing it with faster and faster electrons, let's say, right? Or high energy photon. You can have a photon here that interacts with this quark, picking it considerably. This is something which we can do. Now, for some reason, many of you closed the cameras. I'm not sure why. I would be happy if you reopen them. But it's up to you. Of course, what would happen if we get to higher and higher energies? What will happen? Question for you guys.
Produce more particles?
What?
Produce more particles?
Of course, you would produce more particles. You produce more and more pairs of quark antiquark. But because the will be produced in the direction of the quark that is being kicked off, right? So in the center of mass system, then you'd produce many pairs and many quark antiquark pairs, right? All of them would have momentum in the same direction as that of the That's instead of the original quark, right? Now, many of the new ones, that a new quark, anti-quark that is being produced would be pions and counts. The other ones that would not be pions and counts would decay into pions and counts pretty quickly because pions and counts have the longest lifetime, right? If you produce a row meson, then it will simply decay into pions very quickly, right? So the final outcome of what you're going to get is you're going to get a jet of mesons, which are semi-stable particles, which comes from each quark that has been energized. And these are jets. These are exactly the jets that are being seen if you've seen this, outcome of experiments at CERN and other particle accelerators. That's exactly what is being seen there. All right, you with me? Since many of you, for some reason, decided to close your cameras, then it's more difficult to me to follow whether you're with me or not, but I hope you are. Okay. Now, well, okay. I hope I could finish today. If not, then finish Tuesday, and then we'll do the tutorial on Tuesday and proceed to the next subject. So maybe I should just summarize that and saying when the quark
Did the self disappear for the rest of you as well?
Yes.
Okay.
You'll probably notice in return. Hopefully.
I'll text him just in case. I can use the time when Saf is not here to remind you all of the Astro seminar today at 5, which is about neutron star equations of state, which basically is exploring quark, gluon plasma, and a nucleus the size of a whole star. So would be cool. 5 o'clock.